Alright, today we're going to introduce two variable inequalities, but first I'd like to just do a recap on one variable inequalities. So if you recall, step one is to rewrite the problem in standard form. So we'll just subtract the 100 over. Step two is to either use quadratic formula or factoring, complete the square, some method of solving for x as if this was actually equal to 0. So I just happened to notice right away these were squares. So we have a difference of squares, which means it factors very nicely into 4x minus 10 and 4x plus 10. If we set each of these parentheses equal to 0, we'll get 10 over 4 and negative 10 over 4, which reduces to 5 halves and negative 5 halves. So these represent our two critical values. So next we would make a number line. We would insert our critical values onto the number line, and we would see that there are three possible intervals created by doing this. So we would test each interval. So we have to pick a test point in interval 1. So I'm just going to go with negative 4. A number that's between these two would definitely be 0, and something that's bigger than 5 halves, I'm just going to go with 4. And then what we have to do is take these test points and substitute them into either the original inequality or the standard form version. It doesn't matter. I'll just use the original for now. So we would put in, negative 4 for x, 0 for x, and then 4 for x. And we just want to see which one of these, or hold true. Maybe it's all of them, some of them, one of them, who knows. So we'll go ahead and we'll run this through. If we do 16 times 16, we're definitely going to get something bigger than 100. So this region's going to work. This would become 0. 0 minus 100 is negative, so that region fails. We'll find that if you use 4, that region also works. So I have two intervals that passed my test. So for my answer, I can say any values that are less than negative 5 halves, or 2.5, or any values that are bigger than 2.5 will work. All right, number 2, same concept. We want everything to be on one side so that we have 0. Now, I am not a fan of fractions, so I'm going to go through and I'm going to multiply everything by 5. And when I do that, I get 5, negative 1, and negative 15. I could try to factor it, however, I don't think it's going to be very pretty if I try that, so I'm just going to jump to the quadratic formula. So we'll put in our negative b, our b squared minus 4ac, all over 2a. And if we clean that up a bit, we get 1 plus or minus root 301 all over 10. And 301 does not simplify in terms of radical, so that's as simplified as it gets. So we have to remember that we're going to have to turn these into workable numbers. Like, we're going to have to put these on a number line, so it's probably easier if we convert this into decimal form. So these answers would be about 1.8 and negative 1.6, rounded, of course. So then I'm going to make my number line. And I'm going to use, I think I'm going to use this version, the standard form version, just because I don't like fractions and I really don't want to work with them. I'm going to use this one to run my test points through. So I'm going to put my negative 1.6 and 1.8 on the number line. I'm going to test 0, negative 2, and 2. And of course what you see is 0 is going to work, but just in case, this would be the setup. So you run that through and you'll find that that does not work. 0, 0, negative 15 is less than 0, so that one does work. And then the most outer region is going to fail. So the middle region works, so I want to say anything that's greater than negative 1.6, or anything that's less than 1.8. And I actually need to adjust this. Whoops. So we should have this one first, and then we should have this one. So I actually always use radical form when presenting my answers. So I want to say anything that's greater than the first critical value, which is 1 minus root 301 all over 10, and anything that's less than 1 plus root 301 over 10 will work as a solution in this inequality. So that's what we've been doing. We only had to figure out what x values make this inequality true. It gets a little more complicated once we introduce y values because y is dependent on x. So if x changes, so does y. So the only way that we can show all possible solutions, and there's going to be infinitely many, is to use a graph and to use shading to represent solution regions. So it's been a while, but if you may recall from Algebra 1, you did this with lines. And one of the things that we talked about was if you have a less than or greater than sign, we do a dashed line. Solid line means or equal to. So I know right away for letter A, I'm going to have a dashed line, and for letter B, I should have a solid line. Alright, so the first thing I'm going to do before we begin is realize I think I actually want to start with just a very basic parabola. So we're going to change this problem into y plus x squared, or excuse me, y is less than positive x squared. So just like a one variable inequality, we want to start by pretending that this says equals. So treat it as if it said y equals x squared. So the first thing you would do is graph that parabola, and that's the parent function of the quadratic family. So I know that 0, 0 is going to be on it. If I put 1 in for x, I get 1 out. If I do its reflection, I can just mirror it, get another point. 2 squared gets me 4, mirror that. 3 squared is 9, mirror that. So we get ourselves a nice pretty parent function quadratic. Now before I go ahead and connect it, this is where we got to be super mindful. This does not say or equal to, so we want to actually use a dashed line to represent that, or a dashed curve, if you will. And what that dashed curve symbolizes is points that are on the curve itself cannot count as solutions to this problem. So for example, the ordered pair 1, 1 will not satisfy this inequality. If this were a solid curve, then that means that these ordered pairs would suffice as solutions to the problem. The next thing we need to do is train our eyes to realize this always divides the problem into two regions. We have region 1 and we have region 2. So we have the region that's inside the parabola and the region that's outside the parabola. All we need to do is simply pick a point in either region. It does not matter which one you choose. So you can choose a point that's in region 1 or a point that's in region 2. I like to use 0, 0 a lot, however, that's in neither region. So we can't use that to test a region. So let's just use the point 0, 3, just, for practice sake. Those are pretty numbers to work with. It shouldn't be too terrible. And we're going to put those numbers into our inequality, and we're going to see if it's true or false. So 3 goes in for y, 0 goes in for x, and again I changed the problem to say plus, not that it's going to matter, but it should be plus. And then we ask ourselves, is that true? Well, 0 squared is just 0, so I get 3 is less than 0. Clearly, that's false. So region 1 fails. So we need to realize that the region that's inside the quadratic does not pass the test. If one point fails, then all these points in here will fail. But what that does mean is that region 2 passes. So what I'm going to do is shade all of region 2. This represents all solutions to the problem. Alright, so we'll do it again for letter B. First thing I want to do is I don't want to have 0 on one side because it's a two variable. I always want to isolate y because I'm going to pretend that this says equals. So I want it to say y equals and then whatever the problem is. So we'll have to subtract the 18x squared over, and we'll have to divide everything by 9. And that will give us negative 2 and negative 9. So again, we're going to pretend that this says y equals. So you're graphing this parabola. It's a good rule of thumb to graph the vertex first. It gives you kind of an idea of just how low or high this parabola goes. So if we try to compute h using that opposite b over 2a, well, there is no b value, which means your h is always going to be 0. So if you don't have an x term, h is 0. And if we put 0 in for x, we're going to get 0 minus 9, which is negative 9. So I know my vertex is at 0, negative 9. So what I like to do is maybe have two other points, so I can just really find one more and then just mirror it. So I'll choose something small like 1, I'll just put 1 in for x. Again, you can choose any number you want, but 1 seems to be pretty small and easy. So if we put 1 in for x, we get negative 2 times 1 minus 9, and that gets you negative 11. So I know that 1, negative 11, is going to be on this parabola. And I know that it should be frowning because it has a negative a value. So I'll just go ahead and mirror that point, and then I'll go ahead and connect with a solid parabola because it does say or equal to. So these ordered pairs actually would count as solutions to this inequality. They would make it true. And just like before, I want to think of this as we have one region and we have a second region. So in this case, region 1 is outside and region 2 is inside. It really doesn't matter if you name these or what you call them. This is just what I called them. And then we're going to pick a test point. So if I can, I use 0, 0 because it is the easiest point, in my opinion, to work with. And I can use it now because it's not on the parabola itself. So if we put 0, 0 into our quadratic, and it doesn't matter if you use the first one, the second one, or the third, these are all equivalent. I'm just using this one because it has less things in it. If we put 0 into that problem, I get 0 is greater than or equal to negative 9, and that of course is true. So I actually always shade the region that's true. So you only need to test one point. If it's true, that's the region you shade. And if it's false, that means that's not the region you shade, so therefore you have to shade the other region. One of these regions is always going to get shaded. That's not changing. So the test point will tell you what you need to do. So in our next video, we're going to take a look at how to handle, what if you have two inequalities in one problem? How do you handle that then? So that's what we'll talk about in the next video.